Yeah. Yes, it works. So, good afternoon, everyone. I'm Siyuan. Yeah, I come from University Cork, Ireland, and my research project is an origami-inspired valve. And the outline of today's presentation is shown here. And we applied origami techniques to the valve applications and created a novel origami-inspired iris valve. We then tackled 5 challenges and conducted model analysis. So in industries like pharmaceuticals and food production, the iris valve is widely used for solid material transfer. However, it lacks the rigidity needed for like heavy loads and flow control. Then we accidentally discovered crystalline origami, which also has a tubular shape, a closed diaphragm, but it needs both twisting and compressing. So the 5 challenges we encountered when applying origami to valves are listed here. First, the combination of 2 motions makes the mechanism difficult to control. Second, this origami design cannot be folded rigidly. Additionally, we need to find an appropriate joint type to replace the folds. Meanwhile, the significant deflection might strongly impact the joint's performance. Selecting a material that matches the joint's characteristics is also crucial. To address the first challenges, we split the crystalline pattern in half and mirrored one of the halves. This eliminates the twisting motion without altering the structural size. We named this modified version RC Ori, which stands for radially closable origami, and we discovered that RC Ori is better suited for precise flow control compared to the original crystalline origami. And the second issue involves the non-rigid foldability. The trajectories of the middle points between each folding units do not align during the folding process. To address this, we disconnected these points, resulting in a rigidly foldable kirigami. And we explored compliant joints. By the way, we replacing the folds with a paper model, but it isn't feasible in engineering. Additionally, applying rigid revolute joints adds manufacturing complexity. And we explored the compliant joints as an alternative, as they require fewer components and can carry a certain load. Here we selected the commonly used outside aerosol joints due to their tunable stiffness. And also to reduce the stress and strain at the joints, we introduced an additional parameter, the base angle. As this angle increases, the folding angle between each panel decreases. Some 3D printing materials are too flexible or too rigid. So through the research, we selected the CPE. It adds panel stiffness while allowing the joint deformation. And the theoretical modeling is based on the virtual work principle. Here is the equivalent spring model and the geometric parameters for each joint. And we established the relationship between actual displacement, folding angle for each crease, and the equivalent spring stiffness. But due to the stiffness analysis, during the stiffness analysis, a buckling point arises due to parasitic compressive motion. Simulation focuses on a single folding unit due to symmetry. Comparative analysis of results is performed with verification through the folding angle assessment. And the experimental validation involves applying displacement and measuring corresponding reaction forces. And also, multiple tests cover 6 orientations of the model, and the comparison of results is followed by verification through diameter analysis. So in conclusion, our work produced a novel iris valve design. We have successfully addressed these 5 challenges encountered in the integration of origami principles with valve applications. This innovative structure can also serve as like energy absorption devices, detection robots, breakers, and more. Yeah, that's all. Thank you.